Special Theory of Relativity. Lecture 4. Four-dimensional interval. Causality. Simultaneity. Part 1. The concept of interval. As mentioned earlier, time and distance intervals in a moving frame of reference vary. However, from these two varying quantities, it is possible to compose a physically important quantity that will not change as the body moves, that is, it is said to be relativistically invariant. This quantity is the product of the square of the speed of light and the square of the time interval, minus the square of the distance. This invariant quantity is called the interval. In the special case of a massless body moving at the speed of light, the interval is always zero, since for such a body, the distance is equal to the product of the speed of light and the time interval. Part 2. Four-dimensional space-time. Since the interval has the dimension of the square of the length, its square root is also called the four-dimensional length, conventionally considering the product of the speed of light and time to be the fourth coordinate of four-dimensional space-time. That is, instead of the usual three-dimensional space and one-dimensional time, relativistic physics speaks of a unified four-dimensional space-time, consisting of three spatial coordinates and one temporal coordinate. Accordingly, each point in such a spacetime is characterized by four coordinates, one temporal, multiplied by the constant speed of light, and three spatial coordinates. In other words, each point is characterized not only by its position in three-dimensional space, but also by the moment in time at which it occupied that position. Therefore, such points are called events. Four-dimensional length is the four-dimensional distance between 2 points in four-dimensional spacetime, that is, between two events. Thus, while distances along the temporal and spatial axes change as a body moves, the four-dimensional distance, interval, remains constant. For this reason, space and time are said to be relative, while the unified four-dimensional spacetime is said to be absolute. Section 3. Non-Euclidean nature of four-dimensional spacetime. As can be seen, the length of a segment in four-dimensional spacetime is not defined as the sum of its lengths along each coordinate. The formula for four-dimensional length, in addition to addition, also includes subtraction. That is, the geometry of four-dimensional spacetime differs from Euclidean geometry. Therefore, four-dimensional spacetime is said to be non-Euclidean. Because spacetime is non-Euclidean, the four-dimensional distance, interval, between events can be not only positive but also negative. In Euclidean space, the distance between points, as we know, cannot be negative. A positive interval is called time-like, while a negative interval is called space-like. Part 4. Condition for the existence of a causal relationship between events. Consider the interval between 2 points events in a system. That is, it is assumed that at some point in time, at some spatial point in the system, one event occurs, and at some other point in time, at another spatial point in the system, another event occurs. By virtue of relativistic invariance, the interval between these events is a constant, independent of the system's velocity. Because spacetime is non-Euclidean, this constant can be either greater than 0, equal to 0, or less than 0. However, if the interval between two events is negative, then these two events cannot be causally related. Because for a causal relationship to exist, the interaction between them, in order to travel from one point to the other in a given time, would have to propagate at a speed greater than the speed of light, which is impossible. Thus, events can be causally related only if the interval between them is greater than 0. When the interval is 0, events can be causally related only if the interaction between them travels at the speed of light. Because a slower interaction will not have time to transmit between two given points in the given time. Thus, the non-negativity of the interval between events is a necessary, but, of course, not sufficient, condition for their causal connection. Furthermore, whether two events are causally connected or not does not depend on whether the system in which they occur is moving or not. This is due to the fact that the magnitude of the interval between events is independent of the system's state of motion. Therefore, causality is said to be a relativistically invariant concept. Thus, the important role of the concept of interval is that it allows us to judge the possibility of a causal connection between events. Part 5. Relativity of simultaneity. Now consider two events that occurred simultaneously in a stationary system, that is, at the same moment in time, but at different points in space. Since the time interval between these events is zero, but the spatial interval is not, it follows from the interval formula that the interval between these events is less than zero, which, incidentally, means that these are causally unrelated events. The absolute value of this interval is equal to the square of the spatial distance between the events, since the time interval is zero. If the system is moving, however, the spatial distance between the events will change, and since the interval must remain constant, the time interval must also change. Consequently, the time interval between two events that are simultaneous in a stationary system will no longer be zero in a moving system. Consequently, events that are simultaneous in a stationary system will no longer be so in a moving system. Conversely, if two events, separated by a negative interval, occur in a stationary system at different spatial points at different moments in time, then there always exists a velocity of the system such that these two events will appear to occur simultaneously in the moving system. Thus, whether causally unrelated events are simultaneous depends on the system's velocity. This conclusion is called the relativity of simultaneity. That is, the simultaneity of events in relativistic physics is not an absolute concept, but a relative one. Note that an exception here is the case when two events in a stationary system occur simultaneously at the same point. Such events remain simultaneous and occurring at the same point in a moving system as well. However, these events are not causally unrelated. Now consider the case of causally related events, i.e., the interval between them is positive. Naturally, in any system, regardless of its motion, such events can only be simultaneous if they occur at the same point. Because, being at different distances, no simultaneous events can be causally related. However, an analysis of the type of interval suggests another possibility for such events. Specifically, there exists a velocity of the system's motion such that these two events will appear to occur at the same point in space, but at different moments in time.